Are we on? All right. Welcome, everyone. So today we're going to get started talking about these kind of other topics. So we're going to use what we've discussed so far in class in terms of these different thermodynamic quantities, how one calculates their changes from these infinitesimal changes in internal energy and enthalpy and Gibbs free energy and Helmholtz free energy, blah, 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 right? We're going to use a lot of those concepts and ideas and equations and start applying them to aspects of chemistry. I'm going to first talk about phase equilibrium for pure substances, okay? And then we'll eventually expand on that to talk about phase equilibrium with mixtures, phase diagrams for mixtures of substances, relate to kind of ideas of distillation and such. And then we'll eventually get to other aspects of chemistry, electrochemistry, and other things. So, yeah, any questions people have about anything? We'll get going here. Yeah. No, you can ask me right now.
So, on like when you're interpreting the phase diagram for water, are there like a maximum number of triple points?
So no, so the phase diagram for water, for those who have not watched the video yet, you'll see that there are many solid phases of water, many different forms of ice. Okay, and it's a very phase diagram of water is a very hot topic, or I don't know, hot topic, but very debated topic in chemistry. Okay, there's conferences and sub-conferences and things people discuss in water all the time. While you think we know everything about water, water is something that's still very well studied and discussed by a lot of prominent scientists. And so, yeah, so water has many different forms of its solid phase, and water is not the only one. There are plenty of substances, molecular compounds that have different solids, different solid phases. Okay, that you classify them as being different phases by a variety of different things, whether it be their packing, how the structure of those phases, the heat capacities, or other type of properties in the phases. So different ways you can classify different phases. But anyways, right, and so because water has these different phases, there's different locations of phase boundaries where there can be potentially 3 phases in equilibrium with each other, right? Which is what your triple point is. And basically, there can be as many triple points as you want on a phase diagram, as long as you have like enough different phases, right? So like between 3, like in our typical phase diagram of, I just kind of pull it up here. We'll get back to all that stuff, right? Or like normal phase diagram, right? If I have just a solid, a liquid, and a vapor, right, a gas, right, there's only one point, because there's only going to be one point where all 3 of those phases are in equilibrium, right? But if I have a 4th phase, then there can be at least one more triple point, maybe more, depending on kind of where that phase pops up, right? Where 3 different phases are in equilibrium at one point, right? But so for a given like set of phases, for a given set of 3 phases, there's one triple point. But if I have 10 different phases, right, then I can have a variety of different set of 3 phases that could be in equilibrium with each other that each would then have their own unique triple point. That kind of makes sense, right?
So like on a diagram, between 3 phases on the diagram, they're going to be
Yeah.
on the whole substance.
Oh, shoot. Yep. Went way too far. I was trying to see if I had phase diagram of water here.
It's somewhere.
Yeah, there you go. Let me share that. Those here on Zoom. So, right, there's many different phases here for solid water. Okay, these Roman numerals trying to specify between some of them, right? Right. So there's your normal triple point between solid, liquid, and vapor. Okay, but then there's all the other potential triple points. Okay, between say 3 different solid phases, right? So, yeah. Right, each triple point has a unique set of 3 phases that are in equilibrium for it. Okay, so there's no 2 triple points that have the same 3 phases in equilibrium. And for a single component system, right? But again, if I have many different phases, I can have many different triple points. But again, each triple point has its unique set of 3 phases that are in equilibrium. Yeah, so each line is representing a phase boundary, right? And so, right, if I could try to zoom in this region here, right, you'd see, these kind of dots, right, number of different places where you have 3 of these phases in equilibrium with each other. Okay, but each dot will correspond to 3 different phases that happen to be in equilibrium with each other. Okay, right. So like this point up here, I can do annotate, right? I can circle this, right? So this, oh, great. It's a horrible color for it to default to. Right here, right? This point right here, right? You have a liquid and 2 different solid phases in equilibrium with each other at this point. Okay. Right, you have the solid phase VII and solid phase VI and the liquid all in equilibrium with each other at that triple point, right? And so you have 3 different phases in equilibrium. Okay. But again, those 3 phases are different from, say, this triple point down here, which has the solid, liquid, and the vapor phase in equilibrium. Kind of help answer that question. Great. Any other questions about anything? All right. All right. So, right, what we're going to get into, right, today is start talking about these phase diagrams and interpreting them. And some of this will be review. Some of this might be a little new, depending on your chemistry classes, okay? But when we talk about these phases and phase changes, okay, right? Right. So first we're going to deal with pure substances. So no chemical reactions, right? Single component things, right? But when we're talking about these phase changes and such, okay, as I mentioned last time, this quantity here, the chemical potential, right? U here's the chemical potential, right? That chemical potential, okay, is very important when talking about phases and which phases are stable and phase boundaries and location of those phase boundaries, okay? Because it's all determined by the chemical potential, okay? Because it tells us, chemical potential tells us the most stable phase. And in general, right, what phase is most stable is the one with the minimum chemical potential, okay? And in constant temperature pressure conditions, right, that chemical potential, right, is related to change of Gibbs free energy with the change in number of moles. You can also think of as sort of the molar Gibbs free energy, right? So molar Gibbs free energy, GM, is just G divided by N, okay? So that right? So again, and so why the chemical potential is so important, right, is because it's telling us the sort of, right, the chemical potential for the liquid phase versus the gas phase versus the solid phase, right, is telling us what is the molar Gibbs free energy of that phase, okay, at a given temperature, pressure, conditions, right? And and basically whichever one has the lowest Gibbs free energy is the phase that's going to be the most stable, right? Because if I have something in the solid phase, but the liquid phase chemical potential is lower, right? It has a lower molar Gibbs free energy, right? Then if my substance were to transition from the solid to the liquid phase, the change in Gibbs free energy would be negative, and that would be a spontaneous process. And so that's going to occur, right? And it will spontaneously occur, right? And so again, right, whatever phase is dominant at a given temperature and pressure is because it has the lowest chemical potential at that temperature and pressure. Okay, it is the most stable. Okay? So being most stable means it has the lowest chemical potential, the lowest molar Gibbs free energy. Okay? Right, and so kind of plotting this as a function of temperature here. Okay, plotting the chemical potential versus temperature. Okay, just related to plotting the Gibbs free energy versus temperature, which we talked briefly about how Gibbs free energy changes with temperature with constant pressure. Now we didn't derive an analytical expression. We just got that I want to say Gibbs doing, but it's not the Gibbs doing. But we got the relationship where it was the enthalpy, negative enthalpy divided by temperature squared equals the derivative of the Gibbs free energy divided by the temperature with respect to the change in temperature. Okay. Right, so we have that kind of relationship that tells us how Gibbs free energy, right, the slope of the Gibbs free energy with temperature and things like that. Right, and so, you could use that relationship to kind of get at what these equations look like. And we'll kind of get to some of this later, right? Well, we have these chemical potentials as a function of temperature, right? And for solid, liquid, and gas, right, they have different values. There's different slopes, right? And so their y-intercept, if you will, is different, right? These chemical potentials can be approximated roughly as a straight line, right, with respect to temperature, right? So kind of the y-intercept, right, when temperature goes to 0, right, of these different chemical potentials is going to be different, okay? Right? And we should expect these chemical potentials, these different phases to be different because, again, the chemical potential is related with this molar Gibbs free energy, okay? And the free energy of a solid, liquid, and gas is going to be different, right? Because free energy is related with enthalpy and entropy, right? And, the enthalpy within the solid, liquid, gas phase is potentially a little different because things have different intermolecular forces. Right? The intermolecular forces are the same, but the average distance between your molecules is different, changing the effective intermolecular forces and such. And then entropy is different, right, between a solid, liquid, and a gas, as we've talked about, right? So we should expect the Gibbs free energy to be different in these different phases, okay? And then they have different temperature dependence, right? And as we'll see that different temperature dependence has to do with the different entropy in those different phases, right? So you see gas phase has the greatest temperature dependence, and that's because it has the largest entropy in these phases. And we'll get to that in a minute. Okay? Right? And we note here that when these lines cross, right, at these intersection points, okay, this is where your phase boundary occurs, right? This is when you have the two phases in equilibrium, right? When the chemical potential between two phases equal, those phases are in equilibrium, okay? It's the same thing for chemical reaction in terms of when the reactants and products are in equilibrium with each other. It's when the chemical potential of the reactants equals the chemical potential of the products, then they become in equilibrium with each other. And that's related with the concentrations or the pressures of the reactants and products and mixing. And we'll get to all of that. We'll eventually derive and show where these expressions for your equilibrium constant come from. Based off of chemical potential and its change with temperature and pressure, okay, we can derive your equilibrium constant expressions, okay? And we will do that eventually, right? So again, right, while you have not really been introduced with this idea of chemical potential, it is a fundamental property, fundamental player, if you will, in the role of chemistry, okay? Right, and then again, right, the temperature in which these lines cross, right, there's the transition temperature, right, freezing and boiling temperatures, right, for your cells. Okay. Questions about this slide, this kind of plot here? Again, we'll eventually get to more details of like the actual slopes and relationships of these lines, but now I'm just kind of talking about it qualitatively. Okay. All right. Right, so that transition temperature, right, temperature in which you have two phases at equilibrium, right, and that means that the chemical potential between those two phases are equal, okay? Chemical potential of the two phases are equal, then those two phases are in equilibrium. That is stating the exact same thing. One implies the other, okay? Okay, well, there's no here, right, that you can have some phase that's thermodynamically unstable and can exist in that unstable phase for a very long time. And at room temperature pressure, diamond is an unstable form of carbon. It has a more stable solid phase, graphite, okay? But diamond is never going to convert to graphite naturally, okay? Right? So even if a phase is metastable, right, it's not necessarily technically stable at a given temperature and pressure, does not necessarily mean that a phase transition will occur between those two phases on any sort of time scale, right? Because again, all of this stuff with thermodynamics just talks about what is more stable, what would spontaneously happen given enough time and things like that, but doesn't really talk about how long it will take for it to happen, right? Or in the case of diamond going to carbon, right? We essentially think of that as like it would just never happen, right? Okay. Yeah. All right. So right here is our typical three-phase diagram: solid, liquid, vapor. Okay. Right. As kind of just a reminder, right? We have on these phase diagrams, right? Your phase boundaries, right? There's these blue lines. I'm trying to draw this with the mouse, so bear with me, you know what I mean? Okay, also left-handed, not right-handed, but yeah. Right, and so, right, you have your phase boundaries, okay, that separate your two phases, right? These phase boundaries are when you have these two phases in equilibrium, right? This is when the chemical potential, oh my gosh, right, equals each other. This is awful. See if I well, but I can't do, right, like, I'll just call chemical potentials M or something, right? This is, right, like M, solid, M, right? Those are your two phases are in the chemical potential are equal at those phase boundaries, okay? Right? Okay. And one of the things that I don't know if people have, right? I don't know if anyone's ever done this before or known you can do this with a phase diagram like this, but using this phase diagram, you can read off what the vapor pressure is of a liquid at any temperature, okay, from the phase diagram, okay? And that is related with the phase boundary between the liquid and the gas, okay? So at some temperature, if I go up to that phase boundary, right, mark where that phase boundary is, and then just go straight over, this pressure here is the vapor pressure. Oh, right? That is your vapor pressure at that given temperature. Okay? Right? Because again, if we think about vapor pressure, right? Vapor pressure is, right, when you have this liquid in some container, right? And you know, there's no other things in that container, it's just your liquid, right? And slowly the liquid kind of evaporates a little bit into the gas phase, right? And eventually you get to a point where you have, you know, liquid atoms going to gas phase atoms, and then those gas phase atoms going back down to the liquid. When they bounce and hit the surface of the liquid, they can sometimes get captured and go back into the liquid phase. So you have this transition between liquid to gas and gas to liquid occurring, right? And eventually the rates of those transitions equal each other, okay? And you've reached some form of an equilibrium where the amount of molecules in the vapor phase is constant and not changing anymore, okay? And that, and then those molecules in the gas phase then have some total pressure that they exert, right? And that total pressure they exert is the vapor pressure, okay? Right? And again, that vapor pressure is obtained and occurs based off of an equilibrium that is established between the liquid and vapor phases, right? And so that vapor pressure is determined by this phase boundary, by this, where this equilibrium occurs, right? At a given temperature, where is this equilibrium between your liquid and vapor phase occurring at a certain vapor pressure, okay? And so your boiling temperature, right, your like normal boiling point, right, like T boil, oh you got it. All right, right, your boiling temperature, right, right, occurs when that, right, anyone remember what is the criterion for the temperature in which a substance boils? Yeah, so when the vapor pressure of your liquid equals the atmospheric pressure, right? So the normal boiling point, pretend I, you know, drew this very well, right? That normal boiling point is when, say this is 1 atmosphere. Oh my gosh. I don't know why I keep trying. Right, 1 atmosphere here, okay? What happened to the chat box? Was it? All right, so this 1 atmosphere, oh. Can I move that? Nope, all right, crap. All right, I started playing around with this annotation stuff while doing Zoom and you know, work in progress, right? But, so that 1 atmosphere, right, say your external pressure is 1 atmosphere, right? I guess for the normal boiling point, it's 1 bar, right? But so right, the boiling temperature is when the vapor pressure of your liquid equals external pressure, which if it's 1 bar, right, your normal boiling point. And so to find that temperature, right, you just look at on this phase diagram, right, where's 1 bar, go over, find my phase boundary, and I drop down and read off that temperature, and that is the temperature in which your substance boils, right, under, like, at 1 bar, right? Yep.
Normal and standard, which one's bar, which one's atmosphere?
Normal is bar and standard is atmosphere, if I recall correctly. If someone feels I'm wrong, then you can correct me. I think that's correct off the top of my head. Yep. Okay. And so you can do the same thing if you want to get the sublimation pressure, right? You can look at the solid gas phase boundary and get that exact vapor pressure, right, as you do the sublimation pressure. Okay. Right. And again, right, so you can use these phase boundaries to read off at a given pressure, right, for a given vapor pressure of your liquid, what does the temperature of the liquid have to be at? Or given the temperature of the liquid, what is the vapor pressure of that liquid, right? And that's all related with the phase boundary between the liquid and the vapor, okay? Right, so some other things on this phase diagram, you have, right, your triple point that we talked about. That is where all three phases equal each other, okay? Right? You have your critical point, okay? Point, right, is when is essentially the temperature at which the liquid phase kind of stops existing as kind of a liquid phase, and you reach the kind of this supercritical fluid, which is often kind of thought of as effectively like a gas phase. Yeah. Yeah, those are kind of the main points. Yeah.
Do you ever have a triple point past the critical point?
No, you can never have because if the triple point was somewhere up here, then that would basically mean that your liquid will like never exist. So yeah, so no, the triple point is always going to be at a lower temperature than the critical point, because the critical point is like the triple point in critical points kind of give you roughly the minimum and maximum temperatures in which your liquid can exist. Now that's not quite true for water, because for water, the solid liquid phase boundary doesn't go up to the right, it goes up to the left. So for water, the minimum temperature that the liquid can exist at is not given by the triple point. It's actually somewhere further to the left, lower temperature than the triple point. But for most substances where the solid is more dense than the liquid, the triple point gives you the minimum temperature in which your liquid can exist. And the critical point is then the maximum temperature in which the liquid can exist. Other questions?
What does the phase diagram look for like carbon dioxide?
Question, I think I might have that one here. I know it's on the slides online. It's water, it's more water. Oh, no, I didn't have it in these slides here. So it's one online. So it looks something kind of like this. It's just this triple point is at a temperature and pressure that's, the pressure is higher than, 1 atmosphere, and the temperature is higher than room temperature, like 300 Kelvin or whatever. I forget what it is. I think it's something like 4 atmospheres and 300 and something Kelvin is the triple point for carbon dioxide, which is why carbon dioxide goes from a solid to a gas at room temperature and pressure conditions, because room temperature pressure conditions, you're at this point of the phase diagram. But I mean, the shape of the phase diagram looks the same as this general one here. It's just kind of the location of that triple point relevant to room temperature pressure conditions is, up and to the right, compared to say water, it's down and to the left. Right? I guess the triple point of water. Oh, actually, this might be the phase diagram of carbon dioxide. Yeah. And this is a phase diagram of carbon dioxide. Sorry, the temperature is at 200 something Kelvin. I blew it off. But the triple point is at 5 atmospheres and then 216 Kelvin for carbon dioxide. I'm pretty sure this is for carbon dioxide here, right? And so at 1 atmosphere of pressure, right, gas phase is your stable phase, right? As long as your temperature is greater than, roughly 200 Kelvin or something like that. Okay. And gas is a stable phase, which if you form the solid, you immediately go to gas, right? And you don't go through a liquid phase whatsoever. Okay? The triple point is at a pressure greater than room atmosphere. Other questions? All right, so for a given substance, thermodynamically stable phase at a temperature and pressure, what characteristic? As the greatest density, as the lowest chemical potential, as it gives energy less than 0, it can exist at high pressure, none of these, all of these. What do people think? The most stable phase is the phase with what? Lowest chemical potential, D here, right? Has nothing to do with density, right? All of these phases potentially have a molar Gibbs free energy less than 0, right? Doesn't have to do with that. It's which phase has the lowest molar Gibbs free energy, whether it be positive or negative, right? It existing at a high pressure doesn't matter, right? And so it's B here, right? That has the lowest chemical potential. All right. So here, question, right? Starting with the sample at the temperature pressure conditions of 298.15 Kelvin and 7 atmospheres. What is the first thing that happens when the sample is cooled at constant pressure? Right. So you start off at 298 Kelvin and 7 atmospheres, and you start cooling this thing under constant pressure conditions. What's going to happen? Is it going to go from a liquid to a solid, gas to a solid, liquid to a gas, solid to a liquid, or gas to a liquid? Right, yeah, gas to a liquid, right? It's 298.15 Kelvin is out here, right? Put this gray bar in to indicate where 7 atmospheres roughly is at, right? So you start here, you cool it off. Eventually, you're going to go from the gas phase to the liquid phase, right? And so it's going to be E condenses, right? Goes gas to liquid. Okay. All right. Another version of that phase diagram. Okay. Right. See again, the triple point for water is at a much lower pressure, 0.006 atmospheres. Okay. Temperature is 273.16 Kelvin. Okay, it's the triple point. Again, you have like ice 1, ice 2, ice 3, right? Ice 5, ice 6, and there's many different forms of ice. Right, and you might think like, who cares about these things, right? But you do care because some of these things are relevant. For example, you know, doing deep sea drilling or having pipes run near the bottom of the ocean and things like that, potentially much higher pressure systems situations. And so when ice potentially forms on those pipes, it's not necessarily your normal form of ice. And so if you want something that is going to like kind of be, I'll say, resistant from ice forming on that surface based off of the intermolecular interactions and the packing, the stacking of your solid with the phases of ice and whether or not it's able to kind of stick to it, right? You need to know what phase, what form of ice is actually forming on that surface to be able to know what, you know, what material is going to work best under those conditions, right? Some of these things are relevant to studying, right? What potential forms of ice are in, you know, asteroids or other things like that, right? Right, and so, right, there's different situations, different, you know, physiological conditions that are actually relevant, you know, where these different phases of ice do play a role, and so yeah. There is some importance to it besides just people curious about different phases of ice, right? There are some relevance. Right, and so, you know, given this phase diagram, right, we can ask a bunch of potential things, right? What is the boiling temperature at 1 atmosphere? What's the boiling temperature at 0.5 atmospheres, 1.5 atmospheres? Okay, right, and to answer these questions, right, what would I do? So I'd look at the gas and liquid phase boundary, right? And so if I want to find the boiling temperature at 0.5 atmospheres, what would I need to do given this phase diagram? Yeah, right. So I'd find 0.5 atmospheres somewhere on this here, right? Then I draw a straight line to the right over till I get my phase boundary, and then drop down, and that will be my boiling temperature. Okay, right? And again, you go up to 1.5 atmospheres, go over, drop down, right? I mean, right? And again, the fact that the boiling point depends on the atmospheric pressure, right, is why things like, pressure cookers work, right? Pressure cookers cook things at much higher temperatures because you can get the liquid to much higher temperatures. You can stop it from boiling at, 373 Kelvin, right, if you have the external pressure greater than 1 atmosphere. Because that boiling temperature, 373 Kelvin, is assuming 1 atmosphere of pressure, okay, right? And so you can boil water at much higher temperatures, right, and then cook things a lot faster if you make the pressure much greater than just 1 atmosphere, okay? Similarly, if you were to put water in a vacuum, right, you could boil water at room temperature as long as you reduce the atmospheric pressure enough, okay, right? And, again, that water is boiling at room temperature, so if you touch that water, you're not going to burn yourself. You'll be more than fine because the temperature of the water is room temperature, but it can still boil, right, just because the pressure is low, right? If I want to find the vapor pressure at certain temperatures, right, I just go to my phase diagram, say 600 Kelvin, go straight up, find that phase boundary, and then look over to the left, read off what that pressure is to find what is the temperature that, what is the vapor pressure at that temperature. Okay. So again, that's something, right, that we can use these phase diagrams to just read off. Want to find these vapor pressures, these boiling temperatures, okay? Right, and then if you notice for ice, at least the phase boundary between like ice 1 and the liquid, right, it goes up and to the left, right? And this negative slope means that your temperature in which you melt at actually decreases with an increasing pressure, right? So you push down on ice, increase the pressure on ice at a given temperature, you can eventually get it to melt without changing the temperature, right? And that's not completely unique to water, but it is one of the few substances that does have that type of phase boundary between the solid and the liquid, okay? Because of hydrogen bonding in the water, right, causes the ice to be, the frozen form of water to be less dense than the liquid form. Now, that's not true for all phases of ice, okay? All of the salt phases, we see some ice 5, ice 6 here, right? These are more dense forms than liquid water, right? And it's not surprising that these forms are more dense than, say, ice 1, because you're at much higher pressures, right? So you get to these much higher pressure situations, you can force the solid form of water to not have some of these favorable hydrogen bonding interactions, and instead just try to find the most favorable packing, okay, to create the highest density material in order to compensate for the fact that you have such extreme pressures on your material. So any questions about this phase diagram? Okay.
This might not matter at all, but what would happen if you brought it to that low pressure and just kept lowering the temperature?
So which pressure? Okay. So if I brought my steam, is that what you're talking about? Like what temperature you're starting at here? Or are you changing the temperature or the pressure? So you start at like this low pressure and just increase the pressure at?
No, like you keep the pressure constant.
Okay.
You just lower it would just be ice.
Yeah, it'll just be ice as long as you're starting at like temperature less than 273 Kelvin, right? If you start at a temperature greater than 273 Kelvin, you have a vapor, and as you lower the temperature, you eventually reach the triple point where then you have liquid, solid, and vapor. But then once you lower the temperature even any more, it then all goes to ice.
So
All
they
goes to solid.
just cut off the rest of the truck. I heard it's just
Ice below 200.
Yeah, I mean the pressure down to 0, like, yeah. So, yeah, I mean they cut off down here just because let's see, the next phase diagram, it goes down to, okay, so you go down to like negative 250 degrees Celsius. No, it goes down to like 0 Kelvin, right? So if you keep going, so there's that triple point, you keep going, you'll eventually get to a different phase of ice for water at a low enough temperature at that pressure. And again, the different phase has to do with the different kind of packing of the water molecules in the ice. But each of these triple points has at most 3 phases that can coexist, okay? But you can have multiple triple points in a phase diagram because you have more than 3 phases in a phase diagram. Right. Other questions about these phase diagrams, interpreting them? And some of this should be familiar, right? But maybe not all, okay? So this kind of leads, right, talking about these triple points and things like that, right, leads to what is called the phase rule, okay, which has to do with the number of phases that can be in equilibrium, okay, and the number of degrees of freedom you have given the phases in equilibrium, right? So F here is the number of degrees of freedom, okay, which is the number of variables like temperature and pressure or chemical composition you can change while maintaining whatever phase you are in freely, okay, you can change freely. C is the number of components, right? So a single phase diagram has 1 component, right? Number of different types of molecules, basically, right? And then P is the number of phases in equilibrium, right? So if C is 1 and P is 1, I have a single component system. I have a phase that's, you know, the lowest phase in equilibrium with itself, right? Then the number of degrees of freedom I have are 2, right? Which in our phase diagram means I can change temperature and pressure freely and remain in the vapor phase, right? Within certain limits, right? But like at a given point, I can change temperature and pressure however I want, and I can stay in that vapor phase, okay? But if P is 2, if I have 2 phases in equilibrium and still 1 component, right? I have 1 minus 2 plus 2, which gives us 1. So the number of degrees of freedom is 1, which states then if I want to keep my liquid and vapor in equilibrium, I can change temperature freely, but the pressure has to change accordingly in order to stay on that phase boundary, right? So I have 1 degree of freedom. I can say change temperature or I can change pressure however I want, as long as I change the other variable in the exact way I need to maintain that equilibrium, right? So there's just 1 degree of freedom, 1 variable I can change freely, while the other variable has to be changed, you know, in some specific way to maintain that equilibrium, right? And then in a single component system, right, if P is 3, all 3 phases are equal, I have 0 degrees of freedom, right? That gives us our triple point, right, where I can have all phases in equilibrium with each other, 0 degrees of freedom. I cannot change temperature, pressure, right? It is at only a single temperature and pressure that occurs, okay? Right, and this tells us then I cannot have more than 3 phases in equilibrium at one point in time for a single component system, because that would imply my number of degrees of freedom is negative, which is not possible. Okay, I can't have a negative degrees of freedom, right? The minimum value of F is 0, right? So that minimum value of F of gives us the maximum number of phases that can be in equilibrium at one point in time for a given system, right? Whether it be 1 component, 2 components, 3 components, whatever. Okay. So questions about this phase rule? Okay. Right, the number of degrees of freedom, again, on a phase diagram then kind of determines what type of thing do you have. Do you have like a surface, right? 2 degrees of freedom is like a plane, a surface. 1 degrees of freedom is a line. 0 degrees of freedom is a point, right? Those number of degrees of freedom determine what that shows up on as your phase diagram. Okay. Questions about this? Okay. Then just another example of phase diagrams, right? Right, so here, for example, this is phase diagram for helium. It's more of a unique system. Okay, for helium, the solid and gas phases are actually never in equilibrium. Okay, Solid phase only exists at pressures above 10 atmosphere. Okay. This is technically for helium-4. And why it's special for helium-4 because it has this two different phases of liquids, as normal liquid helium, and then has this superfluid version, okay, of its liquid, which has zero viscosity. Okay? Okay. Right. So again, zero viscosity, right? It has zero kind of friction for flowing. Right? There's no resistance for this liquid to flow and stuff like that. So this thing can flow up over some container that it's in and such, just due to gravitational forces pushing down on the liquid, pushing it up and over and things like that. It's very, very weird. NMR? Probably, I'm not sure which, it depends on basically which isotope is more common. But you are not getting, right, so the supercritical, right, the superfluid, if you look at the temperature, right, is like at pressures, you know, say one bar, right, so normal is fine, but your temperatures here got to be like 1 Kelvin, right? NMR systems aren't at 1 Kelvin, so you're just dealing with a normal, say, liquid helium, and so there it's just sort of whatever, it's going to be a mixture of helium-3 and helium-4. And, you know, it's just whatever kind of isotopic mixture of helium is, you know, from wherever it's harvested. So why this has to specifically be for helium-4 has to do with stuff related to quantum mechanics and the fact that helium-4 is considered a boson while helium-3 is a fermion. And that's helium-4, right? It has 2 neutrons, 2 protons. Helium-3 has 1 neutron, 2 protons, right? And yeah, we'll talk about that in 3340. But yeah, bosons have different properties, fundamental properties than fermions, and they determine a lot of things. Yeah.
Why does the solid not bind this at all?
I'm not sure if that's just because it's not necessarily plotted there, or if it is just it does not exist, sort of below those pressures, right? I mean, the thing is for helium, right? The intermolecular forces in helium are so weak, right? I mean, that's why you need such low temperatures, potentially such high pressures to get these things to form, right? To get solid helium to form, you need very high pressures, right? Because it's just, you know, got such weak intermolecular forces, it's not going to want to form solid. Other questions? Yep.
It's like, that's like 0.6 Kelvin.
Yeah, I mean, so people have gotten things down that cold. People have gotten down to like 0.0 something or 0 something Kelvin. You know, no system's ever been brought down to exactly like 0 Kelvin. No, I don't think it ever will, right? We're never going to reach absolute zero in any experimental apparatus. But, you know, we've gotten pretty darn cold, pretty close. But yeah, so it can be done, cool things off that. The thing is once you get to like, you have to do things like almost like in a vacuum. Problem is, right, is if you have something that cold, you have a gas, like, you know, it's like it's not kind of, right? Well, gas particles will come and collide with your system and transfer some amount of kinetic energy to heat it up, right? And then the other thing, like, yeah, there's different things. And to cool it down, you have to then use like precise kind of laser pulses and other things like that, potentially to try to slow the vibrations and other things down, potentially to help cool it. Like there's, yeah, right? Because normally how we might cool something is by like bringing it in contact with something that's even colder, right? Or maybe doing some expansions of you know, adiabatic expansions of your gas, right? Cool the gas, right? So that's one way things are cooled, right? Is by adiabatically expanding a gas and stuff like that. So there's different ways to kind of cool these things down, but yeah, it's definitely not easy and it's not cheap to get something that cold. But it is possible. It's done. You can Google like, you know, helium superfluid or something like that and watch a video of it and stuff. All right. So what is the maximum number of phases of a pure substance that can theoretically coexist at equilibrium? 3, right? For a single component system, the maximum number of phases is 3. So D here, it is 3. All right. What's the maximum number of triple points that can theoretically exist in the phase diagram for any? At E here, there is no maximum, right? It depends basically on just how many different phases can exist for that single component system, right? So technically there is no maximum number of triple points, as long as you have enough different types of solids or liquids or things like that, right? For your component, right? You can have that many triple points. Question?
When you're saying components, are you talking about like your substance, like mixture or something?
Yeah, so a component is like a molecule, water, sodium chloride, right? Well, any molecule, right? So a single component system is some system that's made up of just a molecule, right? Now, why we use the word component is because it may be like maybe some of the liquid phase, some in the solid phase, or could be in multiple phases and things like that. But it's just one molecule type, right? So yeah, so that's what we mean by component. When we talk about two component systems, right, we're talking about a mixture of like ethanol and water, right? Yeah.
A single component, does water have the max?
I don't know. I don't see why it necessarily would. I know there's a lot of different forms of ice. Now, maybe it's got the maximum number recorded, but maybe that's just because people haven't cared to try to record all the different solid phases of some other molecular compound or something like that, right? But yeah. All right, so let's talk about some thermodynamics here, right? Equilibrium, the chemical potential, right? Mu of a substance is the same throughout a sample, right? So liquid and gas, right, have the same chemical potentials if they're in equilibrium, right? And again, regardless of how many phases are present, right? So at equilibrium, chemical potential of everything is equal, right? It's the same everywhere. Oh, the heck. Right? And so, right, to kind of figure out when those things equal, right, if I'm looking at changes in temperatures and things like that, I want to look at how my chemical potential, right, changes with these different quantities, right? So if I look at the temperature dependence of a phase, let me just make sure, yeah, I didn't, okay, right? I would look at how the Gibbs free energy changes with pressure or temperature, right? So if I look at dg dt, okay, if I divide this entire equation by the number of moles, right, that will give me the molar Gibbs energy and the molar entropy, which is essentially the chemical potential. Right, so change in chemical potential to change in temperature and the constant pressure just equal to negative the molar entropy of that phase, right? Which again is why the slope for a gas is so much greater than the liquid or solid, because the molar entropy for a gas is significantly greater than that of a liquid or a solid. Okay? The slope of this chemical potential, respective temperature. Okay? Right. I want to look at how the chemical potential changes with molar volume, right? Or with pressure, sorry. With pressure, right? Change in chemical potential, change in pressure, it's related with the molar volume, right? Which is sort of the inverse of the density of that material. Okay. Right. So here, these are still plots of chemical potential versus temperature, but they're plots at two different pressures. So I got low pressure, the black line, blue line is at high pressure, right? So you see, right, that right, it's a positive molar volume here, right? So increased pressure, I get an increase in my chemical potential for every phase, right? But for, say, a gas phase, that increase in chemical potential is greater. Or I guess this is looking at liquid and solid, right? Because, yeah, the top form here is assuming that the density of the liquid is less than solid, which means the molar volume of the liquid is greater than the solid. So I have a greater increase in the chemical potential for the liquid than I do the solid. Right? So that where those two chemical potentials equal gets pushed out to higher temperatures, okay, right? So that's why for some substance that has a more dense solid, an increase in pressure causes an increase in melting temperature, okay? But in the case where the molar volume of the liquid or the density, like molar volume of the liquid is less than that of the solid, or the density of the liquid is greater than that of the solid, right? You have a smaller increase in the chemical potential with pressure in the liquid than you do the solid, and that pushes then your, at higher pressures, that actually pushes the melting temperature to lower temperatures, yeah, which is what happens with water. Okay. So again, right, how the chemical potential change of temperature is related with the molar entropy of the substance, and how the chemical potential changes of pressure is related to the molar volume of that substance. Okay? And we will come back to these things. But any questions about these changes, right? How at constant pressure, what is that change in at constant temperature? What is the change in pressure? Here. Okay. Yep. So we'll wrap up with this kind of question for today. Okay, so I want to know, what is the change in chemical potential of both ice and liquid water, assuming, you know, molecular weight, molar mass, 18.02 grams per mole, at 0 degrees Celsius, when the pressure is increased from 1 bar to 2 bar, right? Given the densities of ice and water are 0.917 and 0.999 grams per centimeter cubed, respectively. Okay. And then the second part of this is, what is then the, oh, I shouldn't say delta G. Oh, yeah, yeah. So it is then saying, well, now what is the change in molar Gibbs free energy if I take liquid water, right, or liquid H2O and convert it to solid H2O at 0 degrees Celsius and 2 bar. Second, I thought that was very supportably, but not sure. right? And so we're getting kind of some of this information, right? We're wondering, what is change in chemical potential of the solid and change in chemical potential of the liquid, right? As I go from an initial pressure of 1 bar to a final pressure of 2 bars, right? And so the first question is right, how does that chemical potential change with pressure, assuming constant temperature here? Not assuming, but given constant temperature. Right. What is the change in chemical potential with respect to pressure equal to? Yeah, right. So I mean, yeah. So that's what we want to get to, right? So mu del P, this is the molar volume, right? So right, multiply dP over, right, integrate out, right? Molar volume's constant, so it's just you get change. And mu is equal to Vm change in pressure, right? Okay. And so, right, we just need to find what is the molar volume for our solids and liquids to then calculate this, okay? Right, which again, the molar volume of some compound related to the molecular weight divided by the density, okay? This is 18.02 grams per mole divided by, when I convert this to centimeters cubed, so it's going to be 0.917 grams per liter. If I convert that to liter, centimeters cubed on the bottom, centimeters cubed liter. Right, so I need to multiply that by 1,000, I believe. Okay. And so this is the molar volume of the solid, right? The molar volume of the liquid is then 18.02 divided by 0.999 times 1,000. Okay. And those have to be, let's see here. So the molar volume, oh, so I just already multiplied by the change in, right? So, right. So basically, you take that molar volume, multiply it by the change in pressure, which is 1 bar, and then use the fact that 100 joules is equal to 1 liter bar. Okay, so multiply everything by 100. Okay, and then you'll get this final change in chemical potential of 1.965 joules per mole for the solid and 1.804 joules per mole for the liquid. Any questions about this slide here, right? All right. So, right. So we have like this delta mu S, right? Delta mu L, okay, that we've calculated. Right, and the question is well, what is then H2O liquid, H2O solid, right? What is this change in chemical potential equal to for this phase change at, right, 0 degrees Celsius and 2 bar? Yeah. Right? So know what is that equal to, right? So how might I be able to get that? Yeah, well, so let me ask you this question real quick. What is, so for delta mu, call it 0 here, what is this change in chemical potential for H2O liquid going to H2O solid at 0 degrees Celsius and 1 bar? what does that equal? Yeah, exactly. Right, delta mu 0 here is equals 0, right? Because right at 0 degrees Celsius, 1 bar, these are in equilibrium. So the delta mu here, 0, is equal to each other, right? Which tells me that the chemical potential of my solid at 1 bar equals chemical potential of my liquid at 1 bar, which I'll just call that mu naught, right? Well, the delta mu's that we calculated up here, right? So delta mu S, if you will, was equal to the chemical potential at 2 bars minus mu naught, right? The chemical potential at 1 bar, right? Delta mu liquid is chemical potential at 2 bar, right, for liquid minus mu naught, L solid, right? And so the change in chemical potential for this, right, is what I'm looking for here, right? Delta mu 2 bar, right, is, right, delta mu 2 bar, right? This is specifically, right, the chemical potential of my solid at 2 bar minus chemical potential of the liquid at 2 bar, okay? Now, if I use this equation up above here, I can add mu naught to both sides, right? And I get the chemical potential of the solid at 2 bar is equal to delta mu S plus mu naught. And then the chemical potential of the liquid at 2 bar is equal to delta mu liquid plus mu naught. And so I can plug those in here, right? And the chemical potentials at 0 degrees Celsius, 1 bar, cancel with each other, right? That mu naught cancels, right? So I don't need to know what it is, right? And so this difference here is just delta mu solid minus delta mu liquid, right? So to get the change in chemical potential for this chemical reaction, I just need to take what was the change in chemical potential of my solid and subtract it from the change in chemical potential of my liquid, right? And I'll show those numbers in just a second, but before I flip back to the slides, questions about this, how I got to what I did here, right? Again, when trying to think about answering this second question, right, you can think about what is this specifically asking for? Delta mu here for this phase change, right? It's specifically asking for what is the chemical potential of my solid at 2 bar and what is the chemical potential of my liquid at 2 bar, right? And so it's like, well, I don't really know what that is, but we just calculated the change in chemical potential from 1 bar to 2 bar, okay, right? And then I can use the fact that I know that at 1 bar, those chemical potentials have to equal each other, okay? So I can use that information to then help relate what is the chemical potential at 2 bar compared to, you know, the changes in chemical potentials, right? Given the fact that they have the same starting point, okay? Right, if you're to plot like the chemical potential versus pressure, right? They start at 1 bar, right? They both start at the same point, but they change by different amounts to 2 bar, right? For the liquid and the solid, right? And so to get what is the difference between these 2 points here, right? Which is what's being asked in this question, right? What is that gap between those 2 points, right? I can use the fact that they started here and use the difference between this change and that change to get this change, right? Sort of like taking the difference between 2 vectors to get that thing, right? That's effectively what we're doing, right? I don't know if that helped anybody, but, you know, another way to think of it. Yeah.
You could do like the same process. You had like you told us we had something at
Yeah, if it was initially at equilibrium and then I take it away from equilibrium by changing the pressure, changing the temperature, something like that, yeah, you'd take the changes in chemical potentials of the products minus the reactants to get what the new, you'd get the change in chemical potential of the products minus the change in chemical potential of the reactants, and that would give us the new change in chemical potential of that overall reaction, which is related to the change in the molar Gibbs free energy of that reaction. Right. Right. So just looking at those numbers, right, that delta G mu is equal to the difference in those molar Gibbs free energies, which happens to be a positive 0.16. So here I'm putting delta G sub m is the molar Gibbs energy, right? Again, molar Gibbs energy and chemical potential will be used interchangeably from each other, okay? So I guess just try to get used to it, right? Those are relating to the same thing, okay? The molar Gibbs free energy and the chemical potential are the same thing, okay? So you see here, right, for this phase change at 2 bars, right, we get a positive change in Gibbs free energy, right, which is telling us that, right, this is no longer spontaneous to go from a liquid to a solid at 2 bars, and it's definitely not in equilibrium, right? So again, and that is what we should expect for water, right? As I increase the pressure of water, right, at a given temperature, it no longer becomes favorable to go from a liquid to a solid for that water. Okay. So questions about this problem? So that does it for the slides for today. If anyone has any other questions about these phase diagrams and things like that. So next time on Friday, we'll talk a lot more about the thermodynamics of these phase boundaries, derive and talk about and apply these like Clapeyron equations and Clausius-Clapeyron equations to actually talk about what these phase boundaries look like and their slopes and things of that nature. Okay. Yeah. So any questions, people here or people on Zoom? Yeah. No, homework number 4 is due next week on Friday, and then the following week after that will be exam 2. Yeah. All right. Don't seem to be getting any questions. Oh, there's a question on Zoom. So for this question, we use the first part to answer the second. Yes, exactly. Abigail, we use the second part. So here, let me share screen real quick again. Well, let me just share instead. Let me share this. Right. So in the first part, we calculate these change in molar Gibbs or change in chemical potentials between solids and liquids by looking at how they change with the change in pressure. And then we use that change to get the change in chemical potential between going from a liquid to a solid at 2 bars, okay? But to kind of help us solve that, we use the fact that we know the initial chemical potentials, right, at 1 bar, right, between the liquid and solid are 0, or equal to each other, not 0, so they're equal to each other. Oops, sorry. Right, the chemical potentials are the same at 1 bar. Okay, so I use that fact to kind of simplify this relationship between the chemical potential of a solid at 2 bar and the chemical potential of the liquid at 2 bar to the change in chemical potential of the solid and the liquid from going from 1 to 2 bar. Okay. Hopefully that helped make sense. Yeah, I know. I tried to write things out as best I could here, but yeah, right. But we use the answer for the first part to get the second part, and yeah, I'm happy to go over again in more detail, write things out more, draw things up more to try to help explain how the answers for the first part get us to the second part, if you'd like me to. Okay, that graphic. Okay, yeah. I mean, yeah, yeah, I try to find different ways to present things. But yeah, again, if it's still confusing, I'm happy to go over it more now. Or, if you want to think about it yourself some and go over it later time, I can do that as well. But yeah, just let me know. Okay. All right. All right. Well, thank you, and I'll see you guys on Friday.